of those humble experiences in life where everybody in this room knows more about their land and this region than I will. So what could I possibly have to offer? But we're going to sort of zoom out and look at this from a really kind of large perspective starting off, and then we'll zoom into something a little bit closer to home. Thank the opportunity to come up and share the continuing story of groundwater, which is near and dear to my heart. Okay, so just to start off, of course, everyone in this room knows the answer to this question. Really just want you to sort of hold this in your mind as we're walking through some of the slides and some of the things we'll see today. And really it's, where does your water come from? Now, I do mostly work in an academic world right now, and so you're going to see lots of things that my third year class also sees. They're happy not to be in class today because I'm up here. But anyway, we're going to take a look at the water cycle and take a look at bits and pieces and really just, there we go. I want you to think about which part of this water cycle do you live in? Where does your water come from in it? Is it easily replenished? Of course, we're hearing lots of stories about how some years that's true and many years it's not. That leads us to that third point. How much does it vary? And of course, as we've heard, it varies all the time. So way off on the right-hand side, it's just looking at this typical kind of water cycle diagram, the whole thing starting with condensation, coming down, precipitation, driving the whole thing. You're going to tap into this depending on what you have access to, right? Where you can get something that's decent, that meets your needs. Could be a well, something shown off on the right-hand side there, dugouts, which you've heard a little bit about today already, or maybe you're able to draw off the flowing water directly into your property. That's sort of where we start. The next about 30 minutes or so, our time together, we're going to start off from a very big kind of regional perspective. We're going to then zoom in a little bit closer to some local conditions. Throughout the story, I'm going to talk about major landforms, basically how water moves through them and across them. The focus being to really look at the subsurface in this case, what's happening underground. A couple of examples, we'll look at sources of base flow to rivers, which I've done a bit of work on. Also an aquifer water budget we'll get to, and then end off talking a little bit about soil moisture. Now, the little 3D glasses way off on the right-hand side. This is a full caveat. I'm a geologist by training initially, so we're going to see all this through the lens of a geoscientist, and I suppose that's me, so you're along for the ride. Okay, starting way out. Oh, far too loud. Here we go. Starting way out, Peace River Basin. Okay, start off with this very, very large footprint. Of course, it is a gigantic watershed. Conveys runoff from the mountains towards the east, eventually to the Peace River Delta, and then off to the north as well. Of course, it supports many users along the way, right? We've got users in this room, we've got the environment, we've got lots of things that water moving across this part of Western Canada is going to be useful for. This is a gigantic landscape, right? We're looking at a very large watershed. We're not going to spend a lot of time with this because it's almost too big to fit in your mind. At least it is for me. That's where the idea for the title at least came from when I created it back in probably November or December, thinking about this from more of a landscape perspective. And what does that mean? It's a term that's actually not really used very often. It tends to come from more of the ecology side of things. But the idea being that landscape hydrology is really just bringing together the shape, the landform. What do we know about that when you look at it? Which is called the physiography. The terrain, and how does water move across that and move through that? Again, in your part of the world, you know everything about that, right? We're going to take a look at this from a larger perspective to start, and we'll zoom in a little bit. But really what the term kind of encompasses, and what we're going to see today, is how surface water, groundwater, and climate kind of all fit in this same container. It's all working together. It's all the same water moving through a cycle. So the little image on the left-hand side is meant to remind us that it's all interconnected, right? We're going to see it flash through your fields at some point in time. There's also the very slow flow paths that we'll see moving down into the groundwater zone that could take days, years, millennia, lifetimes basically, sometimes to get to its discharge area, and everything in between. Okay, the next stage of this is we're going to look at some big landscapes and landforms. Now, some of these details might be hard to see. Basically, what I wanted to sort of pause and state at this point is prior to working at the University of Alberta, where I've been for about 5 years, I was a geologist with Alberta's Geological Survey. So I spent 7 to 8 years there, let's say. So a lot of what you're going to see has come from this Alberta Geological Survey. And they're basically tasked with looking at provincial scale geoscience, really big picture questions. And one of the products I'm going to draw heavily on was one I was involved with, setting it up and working with a team to get it off the ground. It was described as hydrogeological regions of Alberta. We're going to kind of change that name today and just think about them as the landscapes. And this is sort of an aside, we were mostly looking at Alberta, trying to understand, we had lots of knowledge of how water moved through different parts of the landscape, very specific studies. Could we come up with something that was more general so that if you were to point to some part of Alberta and say, how does it work here? We'd have at least a starting point. And that's what we're going to see a little bit of today. Now, the map's probably pretty hard to make out, but each of the regions tends to have a very unique characteristic, very unique way of transmitting and moving water through it, which is helpful. It kind of helps set the story for today. Second caveat, I guess, is this point on the bottom. It's going to be pretty similar throughout the Peace River Valley. So whether we're on the Alberta side or heading off towards BC, the geology doesn't care where the border is. It all represents the same sort of thing. So if you're curious about this, and maybe we can somehow get this out to folks, but there's a website where you can go and pick away and look at some of these landforms if you're curious. There's lots of good descriptions, lots of great maps. But again, they're from that perspective of a very large scale. So our first stop, maybe just to back up for a sec. We're going to kind of zoom in, of course, just in the Peace River Valley, which is just a pointer. There we go. Really just meant to show this dotted area kind of over here, which of course is where we are. So our first stop is going to be for this landform that we, creatively called the Western Plains and Benchlands. And really what this represents is you can kind of see this purple color up here, sort of splotched on the map over here. Basically, the sort of more rugged terrain as you're coming off the prairies into the mountains, into the foothills at least. Basically, once you get outside of Grand Prairie, in towards the edge of the province, let's say. Now, maybe take a bit of an aside. This project, when we worked on it, was sort of just starting before that whole COVID thing. And a lot of us ended up working at home and trying to draw things like this and meeting on Zoom calls with about 10 or 12 people to sort out, well, what should this look like? Very challenging and interesting exercise to do when you're working in the basement or whatever. But no, we're going to stay on that one for a sec, sorry. So what we ended up doing was trying to depict what the landscapes would look like. And hopefully, at least in the front half of the room before the bingo board, so you can see some of the detail. And really what's shown on this kind of diagram is sort of a block diagram. It doesn't really have a scale. It's meant to depict ideas. And in this particular idea, we had the bedrock material down below, and of course the terrain and the landscape you're familiar with on the top. The artistry that was brought into it had, of course, like little sailboats and things, which maybe we do have, but probably more like a canoe. And trying to use this as a way to describe how water is going to move through here, right? Very big picture stuff. So for this particular diagram, we've kind of got this nice rugged to rolling terrain sort of shown, if you can see it. Below that, then bedrock. Now, when we decided to draw this particular one, we were really thinking about the Pascapoo Formation, which is a very large geological formation, spans across basically from here, Fox Creek, all the way down to Calgary, actually, right on the edge of the sort of foothill area. Most of that formation's got a lot of mudstone in it, a lot of shale, a lot of things you don't get a lot of water out of. But then there's all these little pockets, these little sort of sand lenses and zones that exist in there that were deposited whenever this formation came down in the Cretaceous. Now, if you're lucky enough to drill into one of those, you get lots of great water, very good supply. But as we've heard already today, you could go from one property to the next, find it there, and not find it in the neighboring adjoining property. So in a diagram like this, that's how we wanted to start to depict it. It's very heterogeneous. It's very mixed. Okay, what else do we know about this region? At least for our prairie terms, it's a relatively moist climate. You get a fair bit of precipitation. Of course, we've got these rugged and rolling hills. And it's really then, this is the headwaters for all the tributaries that are going to drain into the Peace River itself. So the Smoky River, Wapiti, Simonette, all these things that we would have at least in the Grand Prairie area. Now, glaciers did pass by this landscape, of course, recreating it, shaping it, but what they left behind was actually a fairly thin amount of sediment, not tremendously thick. And so you do see areas where you've got nice little gravel patches or buried channels that have been filled in by the glaciers, but they tend to be, maybe in the order of a few tens of meters thick at best. So that sets up then how water starts to move through here. It wants to go down, wants to move into the groundwater, wants to become part of that. But then, of course, is going to be discharging into these lakes, creeks that we've heard about if they're able to be sustained that way. Lakes, I said that already, and wetlands. Okay, let's move forward. So one of the projects that we got involved with quite a few years ago was to start to look at rivers, a little bit larger than the creek size things, in terms of what was their actual source of base flow. So I'm going to take a pause here and sort of move up to this graph way up on the right hand side, and apologies if you're at the bingo boards or beyond, it's going to be pretty difficult to see. But really this is just what's called a hydrograph, and so it represents last year, actually 2024, for measurements made on the Little Smoky River. It's actually down towards Fox Creek, the little orange dot that's here, and then how much flow that river would have had. Now, almost impossible to see where I'm standing, so it's going to be very hard in the room. There wasn't a whole lot of water. You probably know that. There were a few peaks that eventually came in the summer where we got some movement. Fine, that's okay. The black line that kind of runs through here is the long-term average, what you would expect to see at this part of the Little Smoky River based on a few decades worth of information. The part that I guess we were curious about was this really sort of low-lying base amount of flow, the lowest flows, which you don't see as much in the summertime because you've got peaks coming through, and in the spring, it's what you see late into the fall and as you head into the winter. Part of that curiosity was that amount of base flow is what's telling us how this river is connected with the rest of the landscape, right? How much water is actually moving through it. Of course, it's going to be very variable. We know that already. So this base flow then is really the stuff that keeps rivers like this sustained between precipitation events. So if we don't get nice big peaks throughout the winter months, during longer term periods of drought where it tends to be drier, right? It's this base flow is going to come into it. Mostly this is comprised of groundwater, right? So this is water that's just trickling in, seeping in slowly, almost imperceivable. That's going to keep things kind of moving along. And we were curious to see, well, what can this tell us about the sort of broader landscape? Now, this map that's over here is basically that Little Smoky River from the gauge up towards where its headwaters are. And we'll see it's going to change picture in just a second here. So the approach to looking at this kind of thing is we thought, well, yeah, there's a gauge that's there and it's telling us information. That's cool. Could we go up to different parts of the river? That's where all these little extra dots come in. Do a bit of sampling. That's part of where my research comes into things, but really looking at what's in the water. When we go out there at the lowest flows of the year, late in the fall before things start to get too cold, freeze, what do we see? Now, nearly impossible to see. That's me, a colleague of mine that works at a different university, some tubing, and a whole bunch of water bottles and tubes and all kinds of stuff. We're collecting lots and lots of samples for different analyses. And one of the things we're trying to figure out then is, okay, the chemistry, we'll look at that. We're trying to look at how old some of this water might be, a few tools to do that. And we did this not just on the Little Smoky, but we did some work along the Simonette and the Saddle River as well, just to get a feel for how these things worked. Okay, next one. Okay, apologies because this is a little bit tiny. But what we found, at least for the Little Smoky and the other two rivers that we did study, is that that amount of water coming into the base flow time, the low flows, of course, varies as you go down the river. It's not going to be consistent. Okay, that's interesting. There tended to be a lot more groundwater coming into it when the river passed by areas that had lots of sandstone pieces near it in the bedrock, able to move water, right? Didn't see as much coming into it where the landscape was flatter and mostly composed of those sort of shale or mudstone type deposits that just don't move water as readily. So, probably really hard to see up here, but this is one of those rivers with some colors that look like a stoplight. Basically using this water chemistry approach, we could say, yeah, there's parts of it where there's almost no water coming into it at all. It's flagged up here as being red. Just downstream of it, a green part, a whole lot of water coming into it. So we can trace along the river and start to see where it's really well connected to the rest of the landscape and drawing water in. Had a student do some modeling work, and that's kind of what's shown now on this outline of the Little Smoky River. And again, sort of green patches, red patches, yellow patches, like a stoplight, basically indicating and showing, yeah, just looking at it from a fluid movement perspective, we can see the same kind of thing. There's parts that are going to want to gain lots of water and parts that just don't. All fine and good, wonderful science, pretty cool stuff. Actually, let's go back for a sec. But part of it was that we could also see not just that the amount varied, but how old that water was varied as well. To do that, we look at stuff like tritium, right? It was released a ton of that in the 1950s and 60s when bomb testing was happening. You can still see that coming through because groundwater takes a really long time to move. We can also do carbon dating and that kind of thing as well. What we found was there were spots that we had water that was cycling through and getting to that river in less than 20 years, right? A few times, in your lifetime for sure. And then there's other spots where it was actually taking more than 100 years to cycle through the groundwater and discharge into that creek, into that river. So as the river's passing through the landscape, it's not only picking up different amounts of water, it's picking up different ages of water, becoming this big mixture. Okay, not just an academic exercise. So what does this actually tell us? Basically starts to show us that the function of the river, or the rivers, the three that we studied, the water quality, the water quantity, depends on more than just the runoff. So of course, spring happens, we get big pulses, they come through, if they come through, that dominates. But in the long term, function of these kinds of rivers relies a lot more on the subsurface as well. Okay, that's part of the story for the kind of Grand Prairie area. But then if we move to this other color, this sort of tan type thing, a little bit, let's say more towards the northwest of here, also like the Swan Hills, let's say. This is an area that were called regional uplands. Now, as the block diagram starts to depict, basically you get an isolated plateau. These things can be 50, 100 kilometers across, no problem. But basically these isolated plateaus where, unlike the last region, this is where very thick sediments have been deposited. And you see these exist across into Dawson Creek as well and up towards Fort St. John. Now, I have a former colleague at the Geological Survey that was fascinated by why you get gravel on top of these deposits, and there's a really good story attached to that for another time. But you can trace them all around Alberta, and it's pretty cool to see. Anyway, these isolated sort of plateaus then become not only thick sediments where there's lots of stuff on top of the bedrock, but the elevation just helps to capture a little bit of moisture as well. Not tons, it's not the mountains, but it does help then direct some of that moisture down towards the Peace River Valley. Along the way, it can help support small wetlands, feed into some of the tiny creeks that could be year to year, and it becomes the start of those long groundwater flow paths that eventually discharge down in the valley. Now, nearly impossible to see because they're tiny little arrows, but as moisture's landing, infiltrating, finding its way down into the landscape, it's going to begin a journey that eventually discharges down into the Peace River Valley itself. And that can take hundreds to thousands of years. Okay, we've not done a lot of work in this area, so that's about all I have to say about that one. The last part is this western buried valley area. Now, this is really where we're sitting, kind of in this nice blue spot on the map up here. Basically the terrain we would see if you walked outside and had a look. Also looks like this as you head towards Grand Prairie as well. Really characterized by, of course, lots of broad plains, which are very useful for farming, benches, but then as you head down into the river valley, almost like terraces as you move towards lower lying elevations. Now, what's interesting about this area, and it does exist across the prairies into Saskatchewan, is you get these really old valleys that were former versions of a river like the Peace River, way before the glaciers came. They would have carved down into the bedrock and discharged somewhere off into the prairie landscape. And that's sort of shown by these kinds of things here, these big depressions that have cut their way through into the bedrock and then got filled in after the glaciers were here by different deposits. So lots of those. Second thing is, of course, we see lots then of these sand and gravel deposits on these terraces because over geological time, lots of big rivers have moved through this area. So you end up with big packages of sand and gravel that are wonderful for aquifers, but they also, of course, make great aggregate resources, which get mined as well. So if we look at a diagram like this, kind of seeing a very characteristic sort of valley, what it was going to look like. We've got the slumping that's going to happen across over here, these big buried channels. And really it's the combination then of how the climate passes across here, how the climate, terrain, and the soils really support the activities that can happen in a region like this. Okay, next slide. Now, one of the areas that we studied is actually pretty much literally right beneath our feet. And so this is just a map then of this Grimshaw Aquifer, which we're standing on and drinking from today. The star that's right here, I actually put it right on top of the Legion building, so that's exactly where we are right now. Basically, this map then shows the outline of one of these sand and gravel deposits that's very close to the surface. If you're driving in from Peace River, you can actually see it. It sort of rises about 10 meters or so above the rest of the landscape. And it's in a cross section, so if we draw a slice through here with this dotted line, it's going to look something like this. Basically, this red patch up here is that Grimshaw Aquifer. So we're sitting up on top of it. This is very stretched and exaggerated, as geologists like to do when we're drawing things, but it represents one part of a gravel system. As you move down towards the Peace River Valley is another set that's down here called the Old Fort Gravel. And of course, there's the more modern day deposits that we see down there as well. These are all separate, isolated gravel systems representing old versions of the river that would have been through here at a different time. Now, in this area, of course, long recognized as a very productive, useful, shallow aquifer. Questions then coming from the region were, well, will it always be productive? Is it always going to be a good source of water? How will some kind of change, either in pumping, perhaps a different climate, start to affect this resource? Because it's quite sensitive, it's very near to the surface. So we had a little bit of a look at this one too. Now, this was some work that we did with Mighty Peace Watershed Alliance, and you'll hear Adam Norris speak about perhaps some of it after lunch. That was also got some funding through Alberta Environment and Protected Areas because they were curious about the system as well. So we've replaced on the map now, basically showing an image of what the groundwater level would be. So if you have a well in this area, the well has a water level, we can use that to start to figure out what the flow path would look like. So what this tells us is that we got some blue dark colors over here towards kind of upland areas, higher water level, moving water down towards through the lake, and eventually down off into the Peace River. And so it's kind of a mild gradient of water moving through here. In the middle, though, there's this wonderful lake, right? Cardinal Lake, Lake Lac Cardinal, which interacts with the groundwater itself. So I was actually just having a conversation with someone before the break about how this could work. And, really it's just like having a chance during the year in the summer where you've got evaporation, pulling some water out of that lake, and the groundwater is just slowly starting to seep into it to help replenish it. So the whole thing gets set up into this kind of larger two-dimensional sort of thing. The way we took a look at this question was, well, much like a bank account, let's try to do a budget. See if we can quantify or figure out how much, go back for a sec. How much water we have coming in from infiltration in the long term, how much is being pumped out from groundwater users in the area, how much is interacting with the lake, and how much is being discharged from springs as they're trickling out and feeding off into the river valley. Now, no, not yet. Just a little image here down on the lower right hand side. Adam and some other folks were out actually trying to identify these springs on people's properties. So it's just a picture of one of them, classic kind of spring emerging from the ground surface, trickling water into a field. But part of the task here was measuring how much water actually is flowing out of these things. Again, collecting all the chemistry stuff for nerds like me to take a look at more closely, but then putting the whole thing together into this water budget. Okay. So what we see from that is this kind of pie chart up here. I'll read the things out because they're going to be tiny. Half of the water representing the budget is coming from infiltration or recharge, moving down in there. Evaporation from the lake is the orange part of the pie. That's actually fairly significant. Springs are losing water, and then there's some smaller slices of the pie that represent pumping. Altogether, that's what it typically would look like. We started to look at the numbers. I'm not going to get into that too much today. Basically, it's in a pretty good balance right now. Enough is coming in to kind of replace what's being taken out. Now, the evidence of that, and this, apologies for the busyness on this image, but these green dots are where the Alberta government has had long-term monitoring wells. So wells drilled in fields that have been there for decades, measuring water level. The graph that's over here basically has elevation on one side and 40 years worth of information for these particular wells. They all have slightly different water levels, but overall, and so each of these kind of markers is 1 meter, so yay high. For each of these wells, we see, yeah, there's ups and downs, dips and doodles depending on the seasons, on the climate, but overall, they are pretty stable, if you think about it and take a look at that. So, evidence for the fact that things seem to be existing in a decent harmony are the fact that these groundwater levels don't really change too much over the past 40 years. Okay, so again, what does this tell us? Well, for all the withdrawals that are happening here, they're very easily met by the infiltration that's coming into this particular aquifer, which is very interesting. Okay, at this point, you're probably thinking, well, how much infiltration is there, right? You all know about infiltration. You see that in your properties. You see that, in your fields. There's not loads of water floating around. How does it, in this aquifer get balanced? So this depiction, which is very much a cartoon, starts to show like, yeah, in the wintertime we get this accumulation of snow, and right now we're on the pivot point where that's starting to melt, getting this little tiny pulse moving its way down into the groundwater. As we've heard already, it totally depends on what the texture of your field is like, right? If it's heavy, it's not going to infiltrate very much. A little bit sandy, you get a bit of infiltration. The way we tend to look at this from a more sort of geoscience perspective is not year to year, but more like the long term, because that starts to help address water balance questions. But this is really the only time of year that there's going to be enough extra water to get down in the subsurface, become part of that important soil moisture story, and then become part of groundwater. Now, at the same time, this little image down here on the bottom is meant to represent that there's a group at the University of Calgary that we worked with quite a few years ago that developed this computer model to look at it. It's actually built off of Alberta Agriculture's model. Basically, they take these soil profiles and start to look at, well, put a whole bunch of climate information on top and see if we can track how much water moves through what comes out the bottom. The way that they developed it was that they realized across most of the prairie landscape, and apologies, this photo is not fantastic. It's kind of near the Smoky River, but it's merely meant just to remind me to say there's of course little hummocks and dips and doodles in the terrain. And so what they wanted to do was capture the fact that you have small depressions that fill up with snow in the winter, become a pond for a few weeks at the early part of spring, and then disappears as you head into summer months. And so they built this tool to figure out what the infiltration would be if there was no pond, but then also letting some water go down into these ponds and drain in there as well. So sort of like having two estimates tied to the landscape. So it works pretty well for the prairies. Now, a bit of a washed out image, but really this is the upper part of the Peace system before we get to the Alberta-BC border. Peace River is kind of over in this area. What this depicts then is the result of working with a model like that and trying to figure out over the really long term, is there a surplus or not? So the red values, of course, are low. The green values are sort of higher. It's just broken up into smaller sub-basin catchments to sort of get some heterogeneity in here. But all these values are typically quite low. Over the really, really long term, so running these models for like decades, you see that that long-term average goes from about 5 to 10 millimeters a year at most. The red ones are down in sort of like less than 5. Green ones are up, maybe towards 15. But the long-term average, 5 to 10 millimeters a year, thinking about a model like this. So this tells us that if you think about how much precipitation you would get in Peace River, Grimshaw, over towards Grand Prairie, like 5%, tiny amount that gets left over that's allowed to move past the rooting zone down into the deeper flow system. And that's the stuff that drives the flow to move towards wetlands, creeks, and the discharge that we were measuring in some of those streams before. Very small amount. Now, at this point, this is going to start to look a little more familiar. That model and those calculations is the same tool that Alberta Agriculture would use to produce maps like this, your soil moisture report, that you could see month to month if you wanted to track through. They're doing the same kind of thing, basically creating a soil profile, running the weather across the top of it, seeing what comes out the bottom. And so you can generate really cool looking maps like this. This is just borrowed from Saddle Hills County website last year. Basically what it would have looked like in August across the province, what it would look like in July, and you can get snapshots of these month by month, which is a very interesting way to start to look at how soil moisture evolves. So these tools then become something that's easily mapped, maybe can help start to tell us something about soil moisture at a sort of smaller scale. Now, smaller scale is a little bit weird when I look at a map that's got all of Alberta, where the size of your property is somewhere in here at the size of these dots. So, next slide. What this opens the door to, though, is forecasting. This is not an area that I've done too much work in, but I'm working with this company in a different area, doing some research. So I thought I would share it. This example comes from the Manitoba Forage Grassland Association. I believe there's a Agriculture Canada component to it as well. And what they've done is actually partnered with this company called Aquanti. So it's a software company where geoscience and engineer folks have basically created these sort of models. But what they're doing is partnering with groups to really look at detailed soil moisture and forecasting what that could look like even just a few weeks in advance. So it's early days, but it looks pretty cool. So these are just a couple of screen grabs from sort of relatively recent news, field level forecast. There's an app for that, so they can go in and show that they can recreate the landscape in a computer model, basically create a digital twin, if you will, run the weather across it, look at what the soil moisture results would be, use that information. Okay, next slide. Now, I did have a little bit of a play with it last week when I was putting this together, and this is a little bit hard to see, but basically you can go in, and this again is for an area in Manitoba, it's not as useful here of course, but what the tool starts to show is for the Assiniboine River Basin that you can actually create an account, you can log in, you can zoom in on these areas, they could be sub-watersheds, or you can actually zoom right into small parcels of land, and from these sorts of simulation models start to look at a forecast, see what would soil moisture conditions look like over the last year, what could they look like in the next month, what could they look like if the climate was changing. Right? You could start to use these sorts of tools to answer some questions and think about the water cycle. Now, noted here, this is like a whole system approach. This is trying to take everything people know about this area and pack it into one digital twin to get some information out. But it's a nice little digital model that starts to show the bits and pieces that are known well, perhaps can become a useful sort of applicable thing at the local scale. Okay, towards the end, some closing remarks about this idea around landscape hydrology. Really, these are these building blocks. That's how I've tried to present them. They're a pretty big picture, but they at least have a chance to show us how things start to work. It gives context. It starts to show us this part of Alberta could be a little bit different than that part, a little bit different from another part. So it's unique in terms of how water is moving through the landscape. Fine. Those bits and pieces of information will get wrapped up into these predictive models that we just saw a brief example of. So all these things together are really helping depict and understand this whole water cycle, which is fairly useful. Now, the tools then can start to be used to look at state of soil moisture, how much groundwater might be in an area, if you were to try to do drilling a well, what could you expect to see, all those sorts of things. So overall, I guess a useful lens to take a look at large-scale hydrologic systems. Okay, that's the end of the story around hydrologic landscapes. Thank you for the invitation to come up and share part of it. Happy to answer any questions.